Plus of the day. The only good thing that only good thing that happens is, I thought it meant it was like 188. So I you know, 3 days. So you got lucky. I know. I didn't just change it for like 3, and then I was like, so like then you could try. It was like Germany had the worst thing, but 240 of UNT. Wait, I'm gonna try to get like 15 off on the original. Oh, like hash and like lunch. That's not the end. Oh yeah. And then I mean everything else when I've done this. I can do this. So like right here. I would say I was probably because they should give us class. They'll be so you can second get lucky. Yeah, I mean, you're. I don't think it's easy. I wouldn't care if I got shot. I thought it was gonna die. You can't take that. He even admitted it. He was like, guys, go to page.
Mr. Yang, does that dydx mean like the derivative of that? Or what's the apostrophe?
That's right. Yeah, that's the means of derivative.
Okay.
So today we're going to practice. Well, we're going to talk about finding a second derivative of parametric equations. So parametric equations are just equations that have a third variable instead of x and y. We're now the third variable that is variable t. So if I want to find the second derivative of a parametric equation and we want to represent our derivative in terms of x, so ultimately we need to find the derivative of dy dx, right? That makes sense, right? Find the derivative of dy dx. But if we were to go through and expand all this out and work the way that it's supposed to be doing, ultimately, this second derivative is going to feel a little strange because we're going to have to find the derivative of dy dx divided by dx dt. So it's almost like we're taking the derivative, but with an anchor of x prime. Okay? So when we find the derivative of dy dx, we're going to have to include another divided by dx dt. And this is what feels a little bit strange here. It feels like, oh, this should be enough. But we essentially are finding the derivative of y with respect to x, and then dx dt needs to be in the denominator. So we'll practice a little bit, so that you guys can get that comfortable with that, dealing with including that denominator portion when you want to get into the second derivative. But ultimately, it's the derivative of y dy dx. As dy dx is prime divided by x prime, and that will give us the second derivative in when something is in parametric form. Okay, so make sure you have that copied down, and then we'll start looking at some of these examples. Everybody good? All right, so here's example 1. Example 1 says, given the following parametric equations, find d2y over dx2 in terms of t. So first things first, we got to get to dy dx. So dy dx feels more familiar. We know how to do that. So we'll find x prime, we'll find y prime, we'll do y prime over x prime. That'll be dy dx. That'll give us halfway through this process. And then we're going to set up to find d2y over dx2. Go ahead and try that. Okay, so y prime is just t. X prime is power rule, 1/2 t to the negative 1/2. If I divide that out, the 1/2 in the denominator is really a 2 in the numerator. And then if I combine the exponents there, t to the first power times t to the 1/2, it's going to be t to the 3/2. So, all right, so we're halfway there, dy dx. And now we need to find the derivative of dy dx with respect to dx dt. So basically, this piece is going to show up again in our second derivative. So we're basically going to find the derivative of this divided by that. All right, so what's the derivative of this dy dx? Not quite 4/3, but yeah, so you have the right idea. We got to bring that 3/2 down. Okay, so 3t to the 1/2. Okay, so divided by what? Yeah, this x prime. Yeah, so this is the piece that feels strange. Like, why do we need to do this? Well, we're essentially finding the derivative of x, or we'll find the derivative of dy dx with respect to dx. That's basically what's happening there. So once you find x prime, you know that x prime is going to be used twice, right? Once to find the dy dx, and also once to involve in the denominator of your second derivative. Okay, so now we can clean this up, and then this will give us our second derivative. Okay, so dividing by 1/2 is the same thing as multiplying by 2. And I can subtract the exponents, or I can move the that negative 1/2 up as 1/2 and add those together to get 6t. Okay, try example 2. Really, we're just practicing this new formula, and it's just going through those steps. Okay, so number 2, same thing. Go ahead and find x prime, y prime, then build out your dy dx. Once you have your dy dx, then to find the second derivative, it's going to be the derivative of this divided by x prime. Oh, so 3 to the 1/2 is a derivative of 2t to the 3/2. Yeah, so basically you're finding the second derivative of the numerator. You just have to involve that x prime again in the denominator of your second derivative. Two, there's your halfway point. Y prime over x prime, clean that up. And you find the second derivative of dy dx, or the derivative of dy dx divided by x prime, and that's your second derivative. Any questions with 1 or 2? Okay, try number 3. Number 3 says at t equals 1, find the concavity. So concavity is dealing with the second derivative. So ultimately, you're just going to make your way down to the second derivative and then plug 1 in, and then from there decide what that number is going to, what information is that going to give you. Right? So you remember, if I have a positive concavity, yeah, so you're either going to say the concave up, concave down. So positive concavity is concave up, negative concavity is concave down. But you're just going to have to, yeah, you'll do that at the very, very end after you find your second derivative. Then you can involve the c equals 1 to further evaluate.
So if f double prime is greater than 0, concave up.
That's right. Everybody good up to the halfway point there, dy dx? Then the second derivative will be the derivative of dy dx divided by dx dt.
Are you gonna have to do a calendar for the rest of the home?
Say it again.
Well, because on Friday you had us do the rest of the worksheet instead of like the textbook problem, which was tonight.
Oh, right. So I'm just gonna do all the problems from your packet. I'm not gonna, I think this unit and next unit, I really don't see the need for us to do problems from the textbook. I think the classwork is sufficient. But eventually I may pull some textbook problems for review for test review packet, but yeah, I find that these problems from the classwork is sufficient. But your homework tonight is not going to include the AP practice. I think there's some parts of it that it's not covered until 9.3. So we'll just do 9.2 in the classwork. But I think because this is the only thing that we're covering, I think we may be able to finish all of it in class. So we'll see. Any questions with number? Keep going. Yeah, I really think that, up until we get to area or dealing with area, a polar region, everything is just going to feel like, oh, I already know how to do this. I just have to put it into the format that the problem wants me to. But you know how to find the derivative, you know how to find the integral, really just applying those concepts you already know into this particular topic. Okay, so page 9. Yeah, so just keep working, and I will show the answers as you guys have, after you guys have a chance to try them.
For number 1, as you go from negative e to the 4th e to negative 4 e to the 4th e.
So the derivative,
Oh,
that says the second derivative of dx.
I forgot.
Yeah, you got it. The second derivative of the numerator divided by x prime.
It's the first one.
Yeah.
Yeah, I did the same thing.
I don't know.
Guys, I think I want to make a slight adjustment. I'm not going to change the calendar, but I do feel like if we can move earlier to that 9.4 prep, if we can buy us, a period and a half to really get comfortable with graphing polar equations, I think that could be good because I do feel like, these next 2-3 sections is just going to feel like, it's not hard. You're just going to do practice and it's going to feel like you already know how to do it. So 5-10 minutes, and I want to introduce the next topic, arc length. I'm not going to change the homework assignment. I'm not going to change the date. It's just if I can get to that Friday topic earlier, like on a Thursday, then we can have 2 days to get comfortable with graphing polar equations. But the calendar stays, homework stays, I'm not moving anything. Just if I can get to covering a new topic earlier, we'll just have some more time to let us digest that topic. Okay, let me show the answers. And for 5, we do need to involve product rule. Any questions with 5 or 6? Okay, if you guys turn to page 16, let me introduce this topic. I like to be half a day ahead if possible, but I'm not going to change anything about the calendar. The homework, classwork, all that's going to still stay in place. Okay, here's page 16. So we talked about arc length, taking that Pythagorean theorem and adapting it so that we can use it for curves. But we can also use arc or adapt this arc length formula for parametric equations. So if we have an equation that's split up amongst x and y in terms of t, then we can adapt it this way. So we see that 1 plus f prime has that Pythagorean theorem identity to it. So when you think of it this way, well, f prime is the same thing as dy dt over dx dt. So what if we were able to create common denominators and able to pull those pieces apart and think in terms of, kind of break them into component form, into x component and y component form. So we don't have to really worry about, oh, this is, I'm worried about a proof on the test, but I just want to kind of show you that connection between this and this arc length and parametric form. You see that Pythagorean or that Pythagorean theorem or distance formula kind of broken down in component form and very kind of has a similar look to it, right? And now it's dx dt squared plus dy dt squared with a square root instead of 1 plus f prime squared. Okay, so let's look at example 1. Example 1 says x, or for each of the parametric equations, find the length of the curve of a given interval. So x of t is cosine, y of t is sine on the interval from 0 to pi. Okay, sure. So your A and B can be in terms of, so your A and B will be in terms of time. So we find x prime and y prime, and x prime, y prime basically represents dx dt and dy dt. So now we have everything that we need. We put it into our arc length formula. Okay, what do you know about sine squared plus cosine squared?
1.
1, and then what's the square root of 1? Just 1, okay. So what's the antiderivative of 1 dt? Just t, right? So once we get that antiderivative, we can plug in our upper and lower bound. And that's our arc length. And this should make sense from graphical standpoint, because we know that sine squared plus cosine squared is just x squared plus y squared. We know it's just a circle of radius 1 with the center at 0, 0. And if my circle is radius 1, then my circumference is just 2 pi r, which is 2 pi. So this answer that we got from a calculus standpoint also makes sense from a geometric standpoint. Okay, see if you can adapt this arc length formula in parametric form for number 2 as well.
I don't have to simplify radicals, right?
No, you don't have to. Okay, I just want to introduce this topic. We can go back to 9.2, number 7. We'll just spend another few minutes before we end class.
Homework is everything up until page 16.
Yeah, exactly. Yeah, homework is just with except the 9.2 AP practice. It's just a packet classwork problem. So really just page 11. Page 12 and 13 and 14, we'll save it for tomorrow. Yeah, so we'll just follow the calendar. So tonight's homework, no AP practice, just the 9.2 classwork problems.